Hey, in this video I just want to talk about what prolog unification is and the general concept. So what it is just a pattern matching mechanism, and what prolog uses it for is to identify if two things are the same thing as each other, or if they're equal, basically. So it's trying to find out if term 1 is the same as term 2, and the confusing part is that with normal programming languages, equals is an assignment operator, which means take the value of term 2 and assign it to term 1. But in prolog, equals means unification, where it's trying to say, look at the thing on the left and the thing on the right, or in general, look at term A and term B and see if they're equal. And if they're not equal, look at a series of rules and work through these rules to find a way to make them equal by performing variable substitutions and things like that. So I'll explain more in detail as we go along. But why do we actually need unification? I've got a basic example here that will hopefully just give you a bit more background info. So I've got a query here. We want to find the price of a hat. So prolog starts at the top of the knowledge base and scans line by line until it finds something that matches with the query. So it will come down here, we'll have a look at the first arguments and see if they are the same thing. Hat and shoes aren't the same, so it will skip this and say, I'm not happy, this doesn't unify with this one, so I'll keep looking for something else that does. Then it will come to this line, and then again it will have a look at the corresponding arguments. So argument 1 is hat and hat, so these are the same thing, so they match. And it will look at argument 2, does the variable price and $10.99 match? Well, there's this rule in prolog that says that a variable can be binded to any value for the purpose of making them both equal each other. So in here, prolog's allowed to take $10.99 and shove it in the price variable. So now $10.99 is here, and now these two things are the same thing as each other, because product hat $10.99 is the same as product hat $10.99. So this is how you end up finding the actual price of the hat, is because prolog managed to match these two things, and therefore unification was successful. And unification therefore allows prolog to decide what to execute and provide a result for. If there's no way to match anything in the knowledge base, then prolog would act all dumb and it would go down to the bottom and it wouldn't find anything, so therefore nothing would get done. So I'll just cover the rules now. So the very first rule is as simple as you can get. It just says that if you've got two plain terms, or atoms as prolog calls them, atoms are just literal constants, I guess you can look at them that way, and they unify to be the same thing if they are the same thing. So an apple is clearly an apple because they're constant things. Just don't overcomplicate it. Apple is an apple, so prolog is happy to unify these two because they match. And if the terms aren't the same, an apple isn't an orange, so prolog can't match these two together, so therefore prolog fails on this unification. Therefore it would keep on searching for something in the knowledge base that does match. But yeah, just keep this in mind that it's literally just if both the terms are the same, prolog matches. If not, no match. So moving on to rule 2. Wrong one again. Rule 2, where are you? Okay, here we go. So this one deals with variables now, and what the rule is here is that if there's one side of a term that's a variable, so here we've got x on one side, it doesn't matter what side it is, but if there's a variable and a term, then the variable takes on the value of the term for the purpose of making them both equal each other. So this just proves again that the equals isn't an assignment operator, because it doesn't matter what side it's on. it's purely just trying to find a match, and a variable can be binded to any value in prolog. So therefore, if we just bind the value of the term to the variable, then they are equal each other, because now apple will be, because apple shoved into x, now apple's on this side, and likewise because apple is shoved into x on this side, they're both apple now, so therefore they're equal. And if there's only one variable involved, it's pretty simple, because it obviously just gets the value of the term. But you might be wondering what happens when they're actually both variables, like x equals y. In prolog, if both sides are variables and you try and unify them together to make them match, then what prolog does is it sets the variables up in a relationship with each other such that they share the same values. So behind the scenes, prolog will give them a shared memory address location. So they'll both refer to the memory address G1. When the memory address G1 changes, both x and y will see this new value, so therefore they share the result. And what this means is that you have this shared memory address location called G1, and you'll have the variables x and y. X and y will refer to this memory location. So when you update the value of G1, now x and y will see this new value. And I'll quickly demonstrate this on the console. You might have to view this video full screen to be able to see this, because I don't actually have a zoom feature on this software. So what we want to do here, I've got this query. It's basically, I'm just mimicking this same behavior here. So I've got x and y here, I'm unifying them together so they share the same memory address. Say for argument's sake it's G1. Then I bind 3 to x, so now the memory address location G1 has the value 3, so therefore y sees 3. But if I said y was, I don't know, 299, then x will also see this value because it's being updated in G1. So whatever's in here, x and y will both have. So if you're familiar with Java or any other object-oriented languages, then it's basically the same thing as this. Person P2 equals P1. Now P2 refers to the P1 person. So if you did P2 dot age equals, I don't know, 30, then if you change P2 age, then the person P1 here will also have the age 30 because they share the same memory, referring to the same memory address. Therefore, they both see the changes that each other make. So that's all there is to rule 2. Just keep in mind that unifying two unbinded variables, they end up sharing the same value, because this is sort of the trick to understanding how the recursion works, as you'll see in some of my other videos. Rule 3 is slightly more involved, but it's just a matter of walking through the rules. So rule 3 involves processing complex terms. A complex term is just a fact that is sort of made up of other facts. So we've got this order fact, and inside it there's the arguments are facts themselves. So you can sort of think of it as this is like an order object, and inside the order object there's this drink, this variable that's storing what type of drink they want and the food, and then we're trying to just see if these two sides are equal. So I just want to go through some more basic examples first to get the hang of it. So I'll start by just going through the very basic example here. So what prolog does is it goes to the first mini goal. I call them mini goals because prolog will do these first, because it's easiest to rule out the most obvious things that can be wrong first before going to the more sort of resource intensive work of lining up the corresponding arguments. So do term 1 and term 2 have the same name, which is called the functor. So all the functor is this here. You can sort of think of it as the function name. So person and person have the same name. So Prolog's like, okay, cool, these two unify. I'm happy with that. And then it goes on to the second mini goal. Do they have the same arity, which is just the same number of arguments? It's just one argument here, and the other side only has one argument. So mini goal 2 is correct. So Prolog can go and now look at the main piece of work that it has to do, which is probably the hardest part in terms of like CPU resources needed. So then it will look at the corresponding arguments. In argument position 1, we'll see it has Robert and Robert. Then Prolog will try and unify Robert and Robert, and because they're just two terms, Robert and Robert are the same thing, so therefore they match. So therefore the third sort of final goal here is true as well. So therefore these two terms unify successfully. And to move on to another sort of example involving a variable, it's pretty much the same process. I'll just remove this. So yeah, variable in Prolog instead, it's just a matter of walking through the mini goals. So do they have the same name? Drink and drink. Yes. Mini goal 1 done. Mini goal 2, same arity, same number of arguments. Coke is one argument, Y is one argument. So they both have one argument. Now we go in to evaluate the corresponding arguments. So Coke and Y. Is there a way to unify these two arguments together? Well, this goes back to rule 2 where we're dealing with variables. So Coke is just a term and Y is a variable. So Y can have the variable have the value Coke binded to it for the purpose of making them both equal each other. So if Y can accept the value of Coke, then they are now equal each other, because all we've done here is we've taken this argument here, the value of the first argument here, and binded it to Y here. So therefore we end up with this. So now the left hand side and the right hand side are equal. And that's pretty much the gist of that. And this last term here is, this last sort of unification here is a little bit harder, but if we just work through the mini goals, both have the same name, order in order. Prolog's happy with that. Goes on to do the second mini goal. Same arity. So this is argument 1, this is argument 2. Two arguments on the left hand side. Argument 1, argument 2. So the mini goals are successful there. So now Prolog goes and evaluates the corresponding arguments. So argument 1 and argument 1. How can Prolog unify these two arguments to be equal? Well, we've got a variable here on the right side, so quite simply Prolog looks at this, and now drink Coke gets binded to X. So X equals this, and now we go on to evaluate the corresponding second arguments. So we've got a variable Y here, which means hot dog here can be binded to Y here for the purpose of making both sides equal. So keeping this in mind, if we fill in the values for the variables now that have bindings, so order drink Coke, because that's what X is, and food is hot dog. So if you just look back on what we've just done, then you can see that the left hand side and the right hand side are now the same because the left hand side hasn't changed, and the right hand side we've filled in the substitutions, so now they're equal. So prolog's happy now, and now knows that these two terms are unified or equal with each other. And that's pretty much my overview. Obviously it can get a lot more complex, but if you just sort of step back and break it down into how prolog processes the rules, you can sort of try and piece it together. And the last thing I want to touch upon is looking at some list unification. And list unification, I like to break it down into a few simple patterns, because over analysing it you can get into all sorts of complicated cases. But if you keep in mind these three simple rules, I think it will make it a lot easier for you to understand going forward in your prolog journey. So the first simple sort of pattern is that you've just got variables in a list here, and prolog is trying to find a way to make these two things equal each other. And again, because we have variables here, you just look at the corresponding arguments, and whatever's a variable, because you've got a term here, the x just accepts the value 1 for the purpose of making them equal. And likewise 2 gets sent to y, and 3 is in the last argument position, so it gets binded to z. So therefore 1, 2, 3 is equal to the other side 1, 2, 3, so prolog unifies these together, so it's happy now. And the next sort of scenario is the classic head and tail sort of pattern. It uses a list destruction mechanism, which is the bar. The bar just means basically the head's a variable name. You can call this anything, but common notation is calling it head, H for head and T for tail. Head just extracts the very first element of a list, and tail extracts every element after head as a list. So head equals 1 and tail equals this. And as I said, everything to the right of the bar gets shoved in a list, which is all the elements after the first element. And you can sort of take this a step further, and you can have more than one variable before the bar, and all this does is extracts single elements in the list. So A represents the first element of the list, B represents the second element of the list, and tail will store everything after the second element. So quite simply, you just have A equals 1, 2, and tail equals everything else as a list. And obviously you can stick as many variables to the front as you want, but the general idea is that you can put more than one variable before the bar. All it does is extract your individual elements out as they occur in the list. But the main reason why the bar is used is it allows you to reduce the original list by an element each time, which is useful for recursion because it allows you to progress towards a base case, because you're reducing this main list by one element each time. Therefore, eventually, if you keep going, the list will be empty, which is commonly going to be a base case. So just keep an eye out for that one. So probably the last sort of pattern that I want to cover is another use of the bar, because you might be wondering how prolog can unify these two together. Because if I go to the console and if I ask prolog what will be the result of these unifying together, prolog will return true, saying that these things are the same. But you might be wondering how they are the same, because we've got a bar here and an inner list, but this side doesn't have any of that. So prolog does some tricks, and it actually simplifies this list further. So the rule is that if you've got a bar with a list following it, the bar actually removes this list and extracts the elements out. So what you end up with is this, just 1, 2, where, so the bar removes this list and unpacks the elements out into its surrounding list, and therefore you have this result, which is the same thing as the left hand side. So yeah, just keep in mind that there's two ways to use the bar. You can use it in the head and tail list destruction way, where it grabs the first element and the rest as another list. But also, if the bar and a list follows the bar, then the bar removes the list and unpacks the elements, creating just a single list with no nests, no inner lists inside it, which you'll see quite a lot when you start looking at other predicates. But yeah, that's pretty much my intro to unification. I hope it clears up sort of any concepts, and yeah, I'll start actually piecing some more videos together in how to actually use unification. But yeah, thanks for watching, and catch you next time.